Today, we are going to discuss a very important tool in vibration measurement, that is logarithmic decrement. Let us see an underdamped vibratory system. Here, a mass is connected to a spring and the spring is attached to a reference plane. Once the mass is displaced a certain distance and released, it will execute a damped oscillatory motion. The governing equation is shown in 1. Now, to get the displacement or the amplitude at any time t, just substitute t equal to t1 in the governing equation. Similarly, x2, that is the amplitude of the vibratory motion at a time t2, simply substitute t equal to t2 in this equation. Now, t2 is nothing but t1 plus td, where td is the time taken for one complete oscillation, that is damped oscillation represented by td. Now, what will be the ratio of the two amplitude x1 and x2? That will be x raised to negative zeta omega n t1 divided by x raised to negative zeta omega n t2, where t2 is replaced by t1 plus td. Now, taking the natural logarithm in the left side, that is natural logarithm of x1 by x2 equal to natural logarithm of e to the power of zeta omega n td. Natural logarithm of e to the power, that is equal to the power itself, that is delta equal to zeta omega n td. Logarithmic decrement delta, that is the natural logarithm of the ratio of the amplitudes of the successive oscillation equal to zeta omega n td. Instead of taking the successive oscillation, we can go for the oscillation between we can take amplitudes corresponding to oscillations x0, xn. That is, n oscillations are there between the first observation and the final observation. Now, x0 by xn equal to x0 by x1 into x1 by x2 into x2 by x3, etc., etc. Finally, xn minus 1 by xn. Each term can be replaced by e to the power of zeta omega n td. That is repeated n times. So it will be n into e to the power of zeta omega n td. Taking the natural logarithm of x0 by xn, that will be n into natural logarithm of e to the power of zeta omega n td. That is, natural logarithm of x0 by xn equal to n times delta, or delta can also be obtained by taking the ratio of the amplitude corresponding to oscillations separated n times, or n times the oscillations are happening between x0 and xn. Delta equal to 1 by n into natural logarithm of x0 by xn. Now let us see how the natural logarithmic decrement is used for the calculation of damping ratio zeta. Damping ratio zeta can be calculated by substituting the value of Td equal to 2 pi by omega d in the standard equation, and again replacing omega d by root of 1 minus zeta square into omega n. That means logarithmic decrement, damping ratio zeta equal to delta divided by root of delta square plus 2 pi the square. That means rearranging this equation and keeping the zeta terms alone in the left side, we will get this corresponding equation. So this is the standard equation to get the damping ratio that can be used the comparison of energy dissipated from a system under different damping conditions. Now let us solve a numerical problem based on the subject we studied. A 750 kilogram mass is oscillating as shown in the figure. Here the amplitudes at 1, 2, 3, 4, 5 points are there. The time taken for one complete oscillation is also given. So how you use this data to get these 4 parameters? First of all, logarithmic decrement is log x0 by x1 or x1 by x2, like that, or we can take a multiple oscillation amplitude. So we are taking 2.3 because initially there will be some disturbance, and in the end the values will be very small. So we are taking the middle portion to get a standard value or a perfect answer for this particular problem. So the solution will be delta equal to 1 by 2 natural logarithm of 2 by 0.3, that will be logarithmic decrement. Similarly, zeta equal to delta divided by root of delta square plus 2 pi whole square, that will give the value of zeta 0.1488. Then how you calculate the damped frequency omega d, that is equal to 2 pi by Td, where Td is available from the diagram. Then we can directly calculate omega d. Then how you calculate the natural frequency? The governing equation is omega n equal to omega d divided by root of 1 minus zeta square, where omega n can be calculated from this equation and the value is 10.02 radians per second. Now let us discuss what are the results available in this particular problem. Zeta is the parameter we need and delta is the intermediate tool to calculate zeta. And zeta, how you calculate is already discussed. Then omega d and omega n, these are the natural frequency and the damped frequency. Always the damped frequency will be less than the natural frequency, because while moving a body in a resisting ambience, the time taken will be more to complete one oscillation. Since the time is more, the frequency will be less. So omega d damped frequency is less than the natural frequency. So today we discuss the concept of logarithmic decrement, how the logarithmic decrement can be calculated by the successive oscillations, or how it can be calculated between the amplitudes separated by say n number of oscillations. Using logarithmic decrement, how to calculate the damping ratio, and using damping ratio, how can calculate the damped frequency, and the comparison of damped frequency with the natural frequency. These are the things we discussed so far, and we will meet with another topic. Thank you.